The first practical task is to measure the forward bias resistance of the diode. Now we've got the cathode, which is indicated by the grey line, silver line on the diode, and we're going to make the anode positive with the red lead and the cathode negative, and measure the resistance on ohms on our meter, and in this case the diode that I was measuring was 20 ohms, and we're going to record that in the workbook. In reverse bias, we've got the red lead connected now to the cathode. So the positive is to the cathode, the negative is to the anode, and we shouldn't get a circuit because that reverse bias diode should block any current that tries to flow. If we look at the meter, the dial, or the pointer doesn't move across the dial, and it's indicating infinity. Now we won't write infinity, we're going to write greater than 2 kiloohms because that's the highest range on that meter. We're then going to test the diode using the diode test function on a digital multimeter, and there's the diode symbol at the bottom there. We put the diode in forward bias connection, and we're going to measure the forward bias voltage. Now this voltage that's indicated is the voltage that the diode will turn on at. So this diode I tested turned on at 0.701 volts, which is very, very close to the textbook voltage of 0.7. The reverse bias voltage, now we know now if we put the positive on the cathode side, then we shouldn't get a connection. And so the meter reads 1. Now this 1 doesn't mean 1 volt or 1 ohm, it just means it's overscale, it's unable to read that voltage, and so it indicates an open circuit. And you're going to record those values there. So record the forward bias voltage, and then hopefully, unless your diode is faulty, then you should get an open circuit, which is what we'd expect in reverse bias. You're going to do it for 3 diodes, so you're going to do the small signal diode, a power diode, and then the Zener diode. So the Zener diode looks slightly different. It's got the rounded corners, the same as its pictorial. Cathode again is indicated by this, in this case, a black line. So you're looking for a line on a diode, and that will indicate the cathode. You're going to build a small circuit using a DC power supply, an ammeter, a resistor just to limit the current, and then the diode. So this diode there is in forward bias because we've got the positive to the anode, and the cathode goes back to the negative. And we've got a voltmeter in parallel across that diode to measure its voltage. When you connect it up in the variable board, then we need to connect those 2 leads into the same set of 5. That lead there and that lead there are connected together. If this lead was 1 down, it wouldn't be connected. So it's only across a set of 5 where there's a connection. And this just gives us a series circuit through the resistor and then through the diode. So the diode there you can see is in forward bias. If we say this is the positive and this is the negative. The setup that we've got a power supply here, comes from the positive lead into our ammeter, from our ammeter to the resistor, through that little series circuit, and then back to the supply. You're going to set your supply to 25 volts, and that's a voltmeter connected across the diode, and what that's showing is 0.8 volts. So we're dropping 0.8 across the diode, and you're going to put that into the workbook. 0.8, we talk about textbook 0.7, so that's very close. You're then going to work out the current that's flowing, and we're going to use this formula, V supply minus V diode divided by the resistance. So our supply is 25, our voltage across the diode we just measured was 0.8, and our resistance is 220 from the circuit. 25 minus 0.8 gives us 24.2, divided by the 220 gives me 0.11 amps. And if we press the engineering button or turn it into milliamps, we get 110 milliamps. Now if we look at the ammeter, it's showing 106.9. So there's our calculated, there's our reading from the meter, and they're fairly similar. We can work out the percentage difference. There's our 110 minus our 106.9 that we measured, divided by 110. If we times that by 100, it gives me 2.8%. So there's a 2.8% error between our measured and our calculated. You're then going to reverse the diode and measure the reverse current leakage. So there's the diode in forward bias. There's the positive through the anode, through the cathode. The current flows. We're then going to reconnect it with the cathode connected to the positive. So it's now in reverse bias. We're going to set the power supply as high as we can. This has gone up to 30.9 and measure the current flowing through the circuit. Now on 200 milliamp scale is 0, no current, which is what we would expect. But we can look at a different scale. We can go down to microamps, but still we're getting 0 current. Now some of you may get some current there, that will be okay. Very low microamps can be expected in reverse bias. Going to record that. My reverse current is 0 amps. Is it similar to expected? Yes, because we shouldn't expect any current in reverse. And all of my values, that 2.8% error, that 0.8 voltage, tells me that that diode is serviceable. So I'm going to ring that part there. If you get any problems here, if we get a big current flowing in reverse, or that voltage across the diode is more than 1 volt, then we might want to say that the diode is faulty, is non-serviceable. So you can do that for the 3 diodes. The Zener diode is slightly different when we look at the reverse voltage, because the Zener diode has a voltage across it in reverse, specific to that diode. It will be manufactured to give us a certain voltage. In forward bias, and this is shown in forward bias, you can just see the cathode below, then we get a characteristic similar to a normal diode. 0.88 volts across the diode, similar to our 0.8 of the normal signal diode, and there's 106.2 milliamps. So its forward characteristics are very similar. In reverse, there's our cathode there, connected to the positive. What we're looking to do is to adjust this voltage on the power supply until we get a current flow. And this has been adjusted to 4.8 volts, and I'm just starting to get current flow, 0.1 milliamp. Anything less than this 4.8 and there's no current flow. I'm going to record that there, 4.8, and the Zener is actually manufactured as a 5 volt Zener, so that's very close. That's within the manufacturer's specification. So again, I would say that Zener diode is serviceable. When you're testing equipment with diodes in, then it's very important not to put a massive voltage like this 1000 volts or 500 volts across the diodes, because they will blow. So when we use an insulation resistance tester and we got it on 500 volts, what we must do is short out or bridge the phase and neutral connections, and then test between the shorted out connections, phase and neutral, and earth. So by shorting them out, it makes sure that we cannot get a voltage across there. There can only be 0 volts across the phase and neutral. We can also use it on a low voltage, so 250 volts, or we can try and short out the diodes internally inside the equipment that we're testing. So if they're shorted out, there's no danger of voltage going across them and blowing them. So 3 ways: short out the phase and neutral, reduce the voltage to 250, or bridge out the diodes within the equipment.